Got it. My name is Cheng. I'm a research scientist at Dartmouth. So what I'm going to present is a new package called PINNICLE, which stands for Physics-Informed Neural Networks for Ice and Climate. So before talking about the machine learning part, I want to give you a quick overview of what ice sheet modeling does or what type of problems we're solving. So basically, as an ice modeler, we're interested in, or ice sheet modeler, we're interested in two types of problems. One is called forward problem. The other one is inverse problems. So for the forward problem, we're usually, we know the ice geometry, we know some boundary conditions, and then we try to solve some kind of physics. For example, in this case, it's conservation of momentum, or we call it stress balance equation. And then we try to solve for ice velocity. And then knowing this velocity, we can use it to update the ice geometry and then predict the next time step of the ice geometry, and then do this again to solve for ice velocity and then iterate. So that's usually what we do for future predictions. However, in this case, for ice sheet, some of the boundary conditions are very hard to measure. For example, these basal friction coefficient or basal conditions. In order to get these basal conditions, we need to first solve an inverse problem. So the inverse problem is basically using the observed ice geometry, using the observed ice velocity, we solve the inverse of this stress, for example, stress balance, which is basically we construct an inverse problem using a adjoint method, and then we minimize the mismatch between the observation and the model and try to find the optimal parameter which match observation. And then solving this inverse problem or this adjoint stress balance equation, we can get a basal friction coefficient or basal condition. And then we can use this parameter in our forward model to do the future prediction, to solve for forward problems. And as you may notice, the way ice sheet model use data are basically restricted or confined by these two types of problems. So you would imagine there are mainly three ways of using data. The first one is for the forward problem, you use it as initial condition. It's an initial boundary value problem. So you use data as initial condition as boundary problem. For the inverse problem, you use the data just to infer the unknown parameters. And the third category is usually we use other type of data to validate our model. However, during this week, we have seen a lot of nice talks talking about all different types of new data in the ocean. We have Argo. At the ice front, we have Plume, and also on the surface, and we have a new satellite, Edge. All these type of new data comes out more and more. And then the question is, how can we better integrate all this data into our model? Not just use it as validation, not just use it as calibrating our parameter, but try to use the information in the data and try to have all this information running together with our model. And with that, I will bring you the next generation of AI-driven model. Okay, I think this is a nice joke, but to be honest, I don't like this term. So I would rather call it ice model built on next generation of new hardware and software. And the reason is we know a lot about the physics for ice sheet model. So we should not really discard all the known knowledge. We should really use that. And on top of that, we have a lot of new data. So how can we integrate the data with the known physics and also utilizing the rapid emerging new technology, the new NVIDIA GPUs, the machine learning toolboxes? How can we just use all this new technology to improve our understanding of the physics, to reduce the uncertainty of our future predictions? So one idea is this physics-informed neural network. It's a neural network. So first we have to build a neural net. And the way we construct the neural net is we use the XY coordinates as the input for the neural nets, and then all the state variables as the output for the neural nets. And for those who know numerical method, you can think about this neural net as a basis function to represent the functional of the unknowns or all the state variables in your functions. So what we're doing is we try to optimize or try to train the neural net such that it learns all the state variables governed by the physics, by the PDEs you want to solve, as well as feed the data. So the way how we do it is we need to construct some loss function in order to train the neural networks, and the loss function contains, it's pretty slow, contains two parts. Doesn't respond. Okay, contains two parts. One from the data. So basically, we give the neural net's observational data we have and try to minimize the misfit between the output of neural nets and the data. And on the other side, we also use the neural net output and calculate or evaluate the residue of a PDE. So basically, as long as we train the neural nets, it's equivalent to say we are trying to minimize the misfit between the data and the output and the neural net output, as well as we try to let the neural net to satisfy, or the neural net output to satisfy the PDE. So this is a general framework of physics-informed neural networks. However, if you think a little bit more, if we have all the data, if we have all the PDEs, it's an overdetermined problem. It doesn't make sense to train such a neural net to learn anything. It won't learn anything, or you don't get anything. So instead, usually what we do is we pretend we don't know something. Or if you recall the first slide I showed, assume we don't know the ice velocity. We can use exactly the same framework, just hide the velocity data, or just pretend we don't have the velocity data, and feed in all the rest of the data, and let the neural nets to solve for the velocity. So in this case, the PIN becomes a forward solver. And similarly, you can do, I don't know why this doesn't respond. You can do the same thing. Oops. Sorry. Okay, you can do the same thing, just hide the unknown, the basal condition, for example, in this case. So then, just depending on what data you provide, the same framework becomes an inverse solver. So it's all about what data you provide for the neural net. And the same framework can be either forward solver or inverse solver. And so this is just an example of how it looks like when we just feed in all the data on top row except the red box. So the red box is a solution from traditional numerical method, ISSM, just for comparison. The middle row is the PIN prediction, and the last row is misfit. You can see the neural net basically learns all the data and find a good inverse solution. As an ice sheet modeler, I can tell you this is a pretty good job, because we care more about the fast flow region, slow moving region, basal friction doesn't matter. However, something interesting come out is, oops, sorry, this pointer is not. If you look at how long it takes to solve the problem, ISSM, or traditional numerical method, solving such an inverse problem, less than 2 minutes. Same problem, neural nets, more than 5 hours. So then what's the point to use such an expensive framework? Well, there are something I didn't tell. So the reality for this type of inverse problem is, actually we don't have enough, or we don't have full observation of the ice thickness. So we only have all those white dots. Those are ice penetration radar data. And wherever in between are interpolations using either mass conservation or basically streamline upwinding or creating statistics. And those are from the bed machine, which is a data product. So if we just only use observational data for the numerical method, it's not enough. But we can do this with PIN very easily, because PIN doesn't care if you have a mesh, if your data is complete. So it will just try to feed all the data you give and try to fill in the gaps using the physics. So actually, this type of dual inversion problem is fairly easy to solve for PIN, but it's pretty hard for traditional numeric method. And that's that. Oh, I think okay. Anyway, a second example is if you have two parameters which are unknown or partially unknown. In this case, I'm showing Pine Island glaciers. So for Pine Island glaciers, we have ice shelf where we know the basal friction is 0, but for the grounded ice, we don't know much about the basal friction. For the grounded part, we kind of have an idea how the ice rheology look like, but for the ice shelf, we have a pretty bad idea. So for traditional numeric method, what we usually do is we invert for one parameter at a time and use it to do an inversion for the other one. Or maybe you need to iterate a little bit. But with PIN, again, it doesn't care if your data is complete. You just give the data and put in the physics constraints, and then the neural nets will, again, learn from the data as much as it can, and for wherever you don't have the data, it tries to feed the physics. A third example is you can easily change your physics. You can use completely different type of physics. And the reason is because the way how neural nets or how all the packages or how the modern packages for solving neural nets, they are all equipped with automatic differentiation. So to get the gradient of your state variables with respect to some other variables is fairly easy. You just need to call one function, and then the AD tool will help you to derive to get the gradient. And you can put almost any type of physics you want into the framework without changing the whole framework. So with this, you can also add more physics. So you can easily couple multiple physics. In this case, I'm showing we couple momentum balance or momentum conservation with mass conservation. And the way how PIN couple different physics are just through the output of neural nets. Because the output decides what states variables are. And they are strongly, or they just represent the unique states variables. And this variable goes into different physics. You evaluate the residue, you compare with data, and then you sum up the loss. So with that, you probably can see there is a modular sort of framework for these. As a user, you just need to decide what data you use, what physics you want, and then you just throw into this framework, and the framework will decide how the neural net look like, and then how the loss function look like. And then with this idea, we have come up with this PINNICLE package. So it basically does what I just said. As a user, you just need to care what data you want to use for the training, what physics you want, and then the rest will be taken care by PINNICLE. And this package is currently publicly available on GitHub. You can use it by just, if you know Python, pip install PINNICLE. It's there. And we have this also a paper just got accepted at GMD for model description. So for the last 2 minutes, maybe, I will just show you one example about science, because so far it's all about how to use it. Okay, 1 minute. Very quickly. Coupling, we're using PINNICLE to couple mass conservation and momentum conservation, try to infer the bad topography for some glaciers in Greenland. And this work is mostly done by Mansa Krishna. She's a grad student in our group. So what she did was try to compare PINNICLE predictions versus bad machine. And I would just tell you the black contour shows where the physics are imposed in both, either in bad machine or PINNICLE. So for bad machine, only those small black contour regions we impose mass conservation. The rest is extrapolation, streamline upwinding, statistics, kriging, etc. So you can see I also overlay some of the flat track data, which are the observation. You can see some regions, we identify troughs, which looks more realistic. Okay, I'll just go like this very quickly. Yeah, some of the features Pinnacle identifies, which I think it make more sense compared to bad machine. Anyway, if you compare the arrow, Pinnacle does pretty bad job, a little bit bad job compared to observations. Some other regions, this is Upernavik, where we have a lot of observations of the eye thickness, where bad machine also uses mass conservation for the whole region. So you see, using Pinnacle, combining mass momentum conservation, you basically get pretty similar results. But still, I want to point out some area where you see there are some discrepancies in the data and a longer trough anyway. And the third region is NARCEP, where we don't have a lot of data. So the bad machine looks pretty messy. And as you can see for Pinnacle, when we use both, we're getting a better job. Okay, so with that, I would like to conclude. It's not magic, and I would say PIN is just another way of solving traditional numerical method. But it has some advantages. We don't want to replace traditional numerical model, but I would more view it as a complementary. So it can solve, for example, if you want to integrate data with physics, with more data, that's a good idea, or filling in the gaps and also testing with new physics and new coupling. With that, I would like to thank you.
Questions? It's on you, Tommy.
Yeah, super cool. This is really awesome work, and I'm super excited to see this coming together. And thanks for putting this together as a package that people can use and build on. That's awesome. You showed at the beginning. I had questions about sort of like the uncertainty quantification aspect of this. You showed at the beginning like a traditional approach with ISSM, and then your Pinnacle solution inferring basal friction. But of course, we don't know the true value of that. It might be that both solutions are equally valid. There have been a number of proposals over the years for how we might use pins to get at better uncertainty quantification. Do you have any current thoughts on whether pins are a promising way to do uncertainty quantification? If so, what methods are useful?
Yeah, I think that's a really good question. So I think it's a matter of where this uncertainty comes from. If it's from the data, if it's from your model, or if it's from both. I would not say pin is a better way, but it's just an alternative. Because again, you almost get free gradient. You can take the gradient of your variables with respect to whatever you want. So basically, uncertainty is somehow the gradient. So by that, it's a good way to think about using pin for uncertainty quantification. But and that's saying if the uncertainty comes mostly from the model. But if it's from the data, I don't have a clear answer actually, because neural nets has a lot of stochastic in it. The training process has stochastic initialization. So all these stochastics basically add into your final solution. Does this final solution, this stochastic in your final solution, is that from your data or is just from the training process? I think it's from both. So it's hard to separate in that way.
Thank you.
Yeah.
Henri?
Yeah, thanks for the great talk. Can you talk a bit about how you deal with the different terms in the loss function? So presumably there's weights on each of the different terms, and can you learn something from which weights are most influential?
Oh yeah, thanks. That's a really good question. So this loss function is a big issue because you have to balance all the terms. You have to balance the contribution of the data and the PDE, and we have been experimenting quite a lot. We have run like more than 10,000 experiments, just try to explore what's the best combination. After all, we found, well, it's pretty simple idea. So you have to scale all these loss functions into the same order of magnitude in terms of the unit system you're using. And then you might need to play with, you might need to emphasize on your PDE or emphasize on your data by multiplying by a factor of 10 or something, depending on the application. So there's no strict rule, because the whole sort of theory behind neural nets are very vaguely defined. So I would not say there's a strict rule convergence like traditional numerical method, but it's mostly based on experiments.
Thanks. All right, Patrick.
Cheng, great talk. I loved your connection between the inverse problems and then the PIN. And building on this connection, arguably, you know, the sort of our conventional inverse problem could be called strong constrained variational data assimilation, and the PIN is in some ways just a form of weak constrained DA, right? So you're actually imposing the model only in a weak sense. And what is the implication for that for climate, since you know, there's ice applications, but then climate applications to using pins for climate application in that framework?
That's a really good question. Actually, I would say, so it's all about how much error you can afford when you do this approximation. It's all about the approximation. Even if for traditional numerical method, it's based on approximation theory, and you basically project all your solutions onto a specific space, and then on those space, error decrease as you refine the mesh, so on and so forth. So you have theory of guaranteed convergence and so on. With neural nets, it's vaguely defined by the neural net space, which is a nonlinear, highly nonlinear functional space. I hope. Maybe it's not a functional space. I don't know. No theory again. So I think it from what the experiments we can see, it basically follows traditional numerical theory. It's you do an approximation. You kind of control. You have basically the loss function is where you explicitly control your error, and then you reduce the error and try to make your functional to fit to match observation. Although it won't match perfectly as traditional numerical method, because you basically impose the data strongly. So in that sense, I think it's kind of equivalent in a way. But again, there are stochastics, so there are some of the stochastics are hard to measure. I don't fully know, to be honest.
Great. Well, thanks, Cheng Gong. Let's thank our speaker again.